Okay, Chapter 7. Let's move into Chapter 7. One of the things that we talked about previously that you were tested on was standard deviation. And you remember, I'm sure, that standard deviation is a measure of risk, and we talked about why. The greater something, standard deviation is measuring how much something on average deviates from its expected value, its mean. Okay, and so the greater the standard deviation, the greater the risk. For instance, if I said that, when I give an exam, the average score on the exam is 75, and the standard deviation is only 4 points, that's a pretty small standard deviation. If the average is 75 and the deviation on average is like 4 points, that's not very much. So the likelihood that somebody's going to score a whole lot less than 75 is not really great, is it? But if I said the average on my exam is 75 and the standard deviation is 25, wow, that's a huge deviation. Not only could you have some pretty large values, that's not really risk. We could have some huge low values, and that's where the risk comes in. So standard deviation, as it pertains to investment, we always say is a measure of risk. How did we calculate standard deviation? Well, the formula actually for variance, the formula for standard deviation, we said that if you take a certain asset, let's call it asset D, and we take it and we subtract the mean of asset D, the average, and I'm going to subscript the first one, R sub D, and I'm going to put a little I, because what we're going to do is look at the returns for asset D over multiple periods. Period 1, period 2, period 3. In fact, we usually say we're going to sum these deviations for I equals 1 to n. Alright? So when we were calculating, I'm going to erase this where it says standard deviation and put variance. If we were calculating the variance, we take each return that occurred in each period, we subtract the mean, and we square that deviation. And we divide by the total number, and that gave us the variance. All right. We remember the relationship between variance and standard deviation. The standard deviation is equal to the square root of the variance. Our notation for variance is sigma squared. So our standard deviation is the square root of our variance, which gives us lowercase sigma. So our standard deviation, we usually let that be denoted by a lowercase sigma, is equal to the square root of the variance. Now go back up and look at the variance formula again for a second. When I've got RDI minus R bar squared, that's simply the same thing as RDI minus R bar times RDI minus R bar, right? And I show you that because we're getting ready to talk about a term called covariance. And covariance is going to look a lot like the variance. The difference between variance and covariance is variance, we're looking at one asset. And we look to see, well, how does asset D vary from its mean? What we're going to look at with covariance are two assets. And we'll have, well, how does asset D vary from its mean at the same time that another asset, let's call it asset E, is varying from its mean? So that's where we're going with this, and I think you'll see the similarities here in just a moment. Well, this chapter talks about, we're going to start talking about combining assets together, right? We can certainly look at assets independently. What's their risk, what's their return? But as investors, we're not likely to hold one asset as our investment, one asset as our portfolio. Instead, what we're likely to do is to form a portfolio. And so I'm going to put return on our y-axis, and I'll subscript it R sub P, P standing for portfolio. Sorry, that's not what I meant to do. let's back up. I'm going to put risk on this axis, and I'm going to use standard deviation, and I'm going to subscript it P for portfolio. And I'm going to put number of securities on this axis. What we will find, if we were to start with one security in our portfolio, one stock portfolio, that the risk of our portfolio is the risk of that one stock, right? For instance, if you've decided to put all your money in ExxonMobil, then the standard deviation of your portfolio that consists all of ExxonMobil would simply be the standard deviation of that stock. But as we add securities together and we start forming a portfolio of multiple stocks, what we find is the total risk of that portfolio will go down. Okay, it'll go down, and it'll go down, and it'll go down. But no matter how many assets that we add to our portfolio, we will also learn that we cannot eliminate all of the risk. Okay, we're never going to drop all the way down to zero, because no matter how many stocks that you add to your portfolio, you can't eliminate this risk below this blue line, which we call market risk. Another name for market risk is systematic risk. It's in the system. You can't get rid of it. Another name for it is non-diversifiable. We can't get rid of it, right? If you were to try to challenge me on that and form a portfolio and try to eliminate all risk by adding all these risky stocks together, you know, after you have like 8,000 stocks in your portfolio, you would realize that your portfolio essentially is consisting of the market. And we can't control market movements. We can't control Federal Reserve movements and fiscal policy and unemployment and interest rates and inflation and changing currency values. We can't control that. We can't control terror attacks, right? And the impact that things like that, world events, has on asset prices. So no matter how many assets we add together, we cannot eliminate all of the risk. But what we can eliminate, we should. And this risk here that I'm marking is the risk that we are going to be able to diversify. We're going to call this risk firm-specific risk. There are certain influences that are unique to the firm at that point. A company may have a scandal. A company may have a good product or a bad product or a bad management decision. Their sales may be down. There may be a lawsuit. Right? That's firm-specific influences that are not affecting all companies at the same time. So that risk is non-systematic. It is diversifiable, unsystematic risk. All right? So that's why, you know, it doesn't make sense that we would hold a portfolio that has all of this total risk in it when we can form a portfolio and eliminate risk. So my next question is then, what really drives the risk reduction? What drives this reduction in risk? Well, I'd say two things, and they are related topics. Okay, and you'll see that one is called correlation, and the other is called covariance. Alright, so let's start with correlation. Correlation ranges from -1 to +1. The value of your correlation. By the way, our correlation coefficient is usually denoted by the Greek symbol rho. Looks like a P, but it's we're going to call that the Greek symbol rho. And rho ranges from a -1 to a +1. If two assets have -1 correlation, it's said to be perfect negative. And if two assets have +1, it's said to be perfect positive. All right. And there is, what we'll say is that there is, if you have two assets that are perfect positive, that means those assets are always moving in the same direction. And if assets are always moving in the same direction, there is no benefit in terms of risk reduction from forming that portfolio. None whatsoever. Because what we're looking for in correlation, in diversification, is that if we're holding a portfolio and one of our stocks goes down, we don't want all stocks going down at the same time, right? We want another stock that's not going down at all, maybe, or maybe it didn't move, or maybe it went up. That would offset some of that risk. But if our assets are always moving in the same direction, there's no risk reduction from forming that portfolio. If our assets are constantly always moving in the opposite direction, that's where we would get maximum risk reduction. So what's really more likely? Well, neither one of these actually. I'm happy to tell you that most stocks are not going to be perfectly positively correlated with another stock. But at the same time, most stocks are not perfectly negatively correlated either. That is, always moving in the opposite direction. Here's 0 right in the middle. Okay? Most of the assets that we're going to look at combining together are positively correlated. I mean, they are, right? Most stocks tend to be influenced by many of the same factors, primarily systematic type factors, right? Which is why we can't eliminate all the risks, because all assets tend to be affected by the same systematic factors, some greater, some lesser, but they all tend to be influenced. So most assets are positively correlated with each other. And again, that shouldn't come as a surprise. When you think about the Dow Jones, every single night on television, on news channels throughout the day, they're reporting what's happening with the Dow Jones average. And the Dow Jones is 30 stocks, right? That's all it is. It's an index. It's an average of 30 large companies. And yet 30 out of thousands and thousands, they're reporting on the performance of 30. And that's because most stocks tend to move in the same direction. Dow it's an indicator. Usually when the Dow Jones is up, the S&P 500 is up. And the market tends to be up. So it's a measure of broad market movements. All right? So let's talk about covariance. Covariance is, when you see the term co here, it's obviously talking about more than one thing. It's going to talk about not just the variance, but how do two assets covary with each other. Let me give you the formula for covariance. And see if it looks like anything you've ever seen. Let's take two assets. Assets D and E. Okay, so let's take the return on asset D during period I, and let's subtract what the average was, what the mean is for asset D. And instead of squaring that, because that looks like our variance formula, doesn't it, so far? RDI minus R bar D. What we're going to do is say, okay, when that one was varying, what was happening with asset E during the same time period, and how did it vary against its mean during period I? And we're going to do that for each one of the periods. Period I equals 1 to n. And then we're going to average. We'll divide by n. So you can see the formula for covariance, which I've just written here, is very similar to this formula up here for variance, isn't it? For variance, we squared the deviation. For covariance, we're not squaring the deviation because we're looking to see how did asset D react and compare to its mean at the same time asset E was reacting and varying from its mean. Okay? So that's the formula for covariance. Let me show you how it relates, though, to correlation. The covariance of two assets, COV, covariance of two assets, let's say D and E, is equal to the standard deviation of asset D times the standard deviation of asset E times the correlation between assets D and E. That's covariance, right? We're looking at basically interaction, right? If we're calculating the standard deviation of a portfolio now, see, if we started with just one asset, let's call it asset D, then the standard deviation of my portfolio was simply the standard deviation of asset D. But if I combine asset D with another asset, we're calling asset E, now my standard deviation has to take into account both sets of volatility, and we can't simply average the volatility, because we need to understand, well, were they volatile in the same direction or not? I'm going to rewrite this, D and E here. Okay, so that's what our formula is showing us. It's showing us the interactive volatility, interactive risk. It's the risk of asset D and the risk of asset E, and the fact or the direction of their movement. Were they moving in the same direction or not? Okay, so the standard deviation of a portfolio is not simply a weighted average. We can't just average the risk, because we have to take into account, were they moving in the same direction or not? Right? What was their interactive risk? Did some risk offset other risk? As a silly example, I'll show you what I'm talking about here. I'm going to give you two assets here. We'll have asset M and asset W, and I'm going to form a portfolio in a moment that has those two assets together, M and W. Okay, let's assume that the rate of return, the average of asset M is 15%, and I'll give you the standard deviation of asset M. I'll just make it 20%. The return on asset W also is 15%, and its standard deviation is 20%. So what's the return on my portfolio going to be? Well, that one's easy. The return on my portfolio is going to be 15%, because if I put some of my money in asset M and it earns 15, and the rest of my money in asset W and it earns 15, then my combined portfolio is going to have a return of 15. But the standard deviation of my portfolio is not necessarily going to be 20, right? Because I have to understand the volatility. Which way were these stocks moving? So I'll show you. Asset M went up and down and up and down. It looks like an M. During the exact same time period, asset W went down and up, down and up. So if I combine these two portfolios together, see, both of these have an expected return of 15, so it's above and below 15. The way I've drawn this, my expected return on my portfolio is going to be 15, and actually I would have no risk, because when asset M lost money, asset W made money. And when asset W was below 15, asset M during the same time period was above 15. So I create this mythical portfolio that would have zero risk, zero variation, right? So the standard deviation of a portfolio is not simply a weighted average, right? We're not averaging the 20% here with this 20%, right? Because we have to take into account correlation and covariance. So let me give you the formula for the standard deviation of a two-asset portfolio. It's not a weighted average, right? So there must be a formula. And there is. It looks like this. I'm going to call it sigma P, because sigma stands for standard deviation. P stands for portfolio. Again, we're using two assets, asset D and asset E. The formula is as follows. We'll take the weight that we're going to put in asset D squared times the standard deviation of asset D squared, which is called the variance, by the way. The weight in asset E squared times its standard deviation squared, plus 2 times the weight in D times the weight in E times the covariance of asset D and asset E. And then we take the square root. Without the square root, without the radical, that would have been the variance of the portfolio. And then we take the square root of the variance and we get the standard deviation. Now I'm going to write, I put it this way on purpose, I'm going to expand that now to be, remember, standard deviation of asset D times the standard deviation of asset E times the correlation between asset D and E. In case you blinked, let's go back and I'll remind you that I showed you right here that if you want to know the covariance between two assets, you take the product of their standard deviations times the correlation. So what I've done is I've expanded covariance, and I'm going to rewrite the formula into the form that I most like working with. Okay. All I did was substitute in sigma D, sigma E correlation for the covariance term. And this is my standard deviation of a two-asset portfolio. Let's take a look at an example. Here again are our two assets, and they are asset D and asset E. The return for each asset, this is in your book by the way, is 8 and 13. The standard deviation of each asset is 12% and 20%. And they give us initially here, or what I'm going to assume here, is that the correlation between these two assets is positive 0.3. I want you to also assume these weights initially, because we've got to know what we're putting in each asset. So let's put 70% of our money in asset D and 30% of our money in asset E. So those are my weights. So plugging into our formula, the weight that we're putting in asset D is 70%. So the standard deviation of my portfolio, I'm going to put 0.7 because that's 70%, and I square the weight times the standard deviation. I'm not going to use decimal. You don't have to as long as you're consistent. 12% squared plus the weight. Of course the weights have to be decimal, right, because they have to add up to 1. 0.7, if that's 0.7, this has to be 0.3 squared times its standard deviation squared, plus 2 times my weight in D, my weight in E, times the standard deviation of one, standard deviation of the other, times, I'm just going to change colors just for a moment, .3. The only reason I'm changing colors is because I do want to highlight the fact that it's just a coincidence that my correlation is 0.3 and this weight of asset E is also 0.3. Those are different 0.3s, right? This first one that I have here, I've got 0.7 and 0.3. Those are the weights. Coincidentally, my correlation here is 0.3. This is going to give me, as I've done it here, this would give me the variance, wouldn't it? This gives me the variance, and if I take the square root of the variance, I get the standard deviation. So I believe if you multiply, I worked this earlier, 0.7 squared times 12 squared, you get 70.56. If you multiply 0.3 times 0.3 times 20 times 20, I believe you get 36. In this last term, if you multiply all these variables together, you get 30.24. Which added together underneath the radical, you get the square root of 136.8, which gives you 11.7%. So the standard deviation of this 2-asset portfolio is 11.7%. We've combined 2 risky assets together. Now you know they're risky, you can tell, because asset D has a standard deviation of 12, asset E has a standard deviation of 20. And if you'll notice something, the standard deviation of our portfolio, of our resulting portfolio, in fact I'm going to write note, the standard deviation of our portfolio, which is equal to 11.7%, it is lower than either of the 2 assets. That is, its standard deviation is lower. Right? One of the assets had a standard deviation of 12, the other one has a standard deviation of 20. We've combined these 2 together, and we've actually got less risk than either of the 2 assets held by themselves. Okay, so I know we had risk reduction. I know we did. We've definitely had risk reduction, and we'll calculate that amount here shortly. Okay, now continuing along. Remember that correlation ranges from -1 all the way to +1. Okay. Also, let's look at our variance, and remember, since we're remembering everything, let's remember that variance equals sigma squared, and I'm going to write that formula. It was WD squared sigma D squared plus WE squared sigma E squared. In fact, it's everything that was under the radical, right? Plus 2 times WD WE sigma D sigma E correlation DE. Again, all I did was rewrite the formula for variance. Variance equals that. And remember, correlation ranges from -1 to +1. Well, it turns out that if your correlation is +1.0, then the right hand side of this equation here for variance, then our variance is a perfect square. In other words, the standard deviation of our portfolio, not standard deviation, I'm sorry, the variance of our portfolio is a perfect square. WD sigma D plus WE sigma E squared. Just as a quick proof. I mean, just you ought to convince yourself of that. You know? So let's knock it out here real quick. WD sigma D plus WE sigma E and we said it's a perfect square, so multiply it times itself, WD sigma D plus WE sigma E, right? Let's use the FOIL method. That's going to give us WD squared sigma D squared plus WD sigma D WE sigma E. You remember what I'm doing? Plus WE sigma E WD sigma D plus WE squared sigma E squared. Right? The FOIL method, where you're multiplying, you know, this times this, and then times that, and this times this, and this times that. Right? And so when you collect it, when you simplify it, organize it, you would get WD squared sigma D squared plus WE squared sigma E squared plus 2 times WD WE sigma D sigma E, and that's exactly what our variance is if, remember, if the correlation is positive 1, because, you know, normally we would multiply this times the correlation between asset D and E, but if the correlation is positive 1, we don't need to include it, right? All right, so your book is pointing this out, that if your correlation is equal to positive 1, then you've got a perfect square. Well, you may think, well, why do we care? Why do we care if it's a perfect square? Okay, well, here's why. So if your correlation is equal to positive 1 and the variance, we said, is a perfect square, let's look at the standard deviation. The standard deviation, as you remember, is equal to the square root of the variance. And so since the variance is a perfect square, which is WD sigma D plus WE sigma E squared, then the standard deviation is equal to the square root of the variance, which then is simply equal to WD sigma D plus WE sigma E, which is a simple weighted average. Now, a moment ago I asked you, is the standard deviation of a portfolio, I don't even know if I wrote it down, let's see, I guess I didn't, but I probably asked, is the standard deviation, no, here it is, you see, I said right here, so the standard deviation of a portfolio is not simply a weighted average, because we have to take into account correlation and covariance, right? It's not. And because it's not, we've got this somewhat complicated formula that we use to solve for the standard deviation of a portfolio. But what we've just shown is, if it's possible, if we could find two assets that have a perfect positive correlation, perfect positive, which is correlation right here, positive 1, then we show actually that the standard deviation is a simple weighted average. Okay, so let's take a look here. Let's use the same information we have. Again, if we assume the correlation is equal to positive 1, let's calculate the risk and the return of this portfolio. The portfolio return will equal a weighted average. 70% of our money I don't even have my numbers here. Let's go back here. The return of my portfolio right here is 8% and 13. So 70% of my money would earn 8. 30% of my money would earn 13. And I get 9.5, I think. Let me try that one more time. Yeah, I get 9.5. So the expected return on my portfolio would be 9.5%. And the risk of my portfolio, as denoted or measured by standard deviation, it would also be a weighted average. And I get 14.4%. So, a lot of things going on here, okay? We've said a few things. Let me go back. I want you to look at when we first talked about correlation, and I need you to grasp this and remember it. Look up here at our correlation line up here. I said correlation ranges from -1 to +1. I said we get maximum risk reduction when the correlation between our assets is perfect negative. We would get the most offsetting volatility. And I said at the other end, on the right hand side, if we have two assets that have perfect positive correlation, look how much risk reduction I said you get. None. There is no risk reduction from forming a portfolio if the correlation between those two assets is perfect positive. There is no risk reduction. So as I go forward, they said, if I told you, let's repeat it, if correlation is +1, there is no risk reduction. If correlation is +1, there is no risk reduction. So here I'm saying if we assume that the correlation is +1, we've just said there is no risk reduction. So 14.4% is, even though it's a weighted average, right? It's a weighted average. There is no risk reduction. All we're doing is kind of spreading out that risk, but we're not reducing risk. Let's compare that for a moment ago when we had, remember, if the correlation was equal to +0.3. You remember a moment ago? Let's go find it. What was the standard deviation when we said the correlation was +3? It was 11.7. Everything else was the same. All we did was had a different correlation. So if the correlation is +0.3, the standard deviation was 11.7%. So we know we got risk reduction. We said it earlier, we know we had to have risk reduction because 11.7 is less than 12. But how much risk reduction did we get? And I say it's the difference between 14.4 and 11.7. Because the maximum risk that we would have with these two assets is 14.4. That's when there's no risk reduction. We combined assets together and said, well, look, the correlation is +0.3. We saw for the standard deviation we got 11.7. So I assert that we had, what is that, 2.7% is the risk reduction from forming this portfolio. In case you can't read my handwriting, it says 2.7% is the risk reduction from forming this portfolio. Alright, now let's look at a different scenario. What if we assume that the correlation between these two assets is perfect negative, which is -1? Well, guess what? The variance of our portfolio simplifies to WD sigma D minus WE sigma E squared. Okay, again, use the FOIL method and convince yourself that it is that. You would end up with WD squared sigma D squared plus WE squared sigma E squared minus 2 times the WD WE sigma D sigma E. Okay, you would end up with the standard deviation of the portfolio that we had earlier. And if you assume, let me go back here for a moment, let's look at our formula for the standard deviation of this portfolio, actually the variance. Let's look at the variance. Kind of hard to see. I don't really have a good pointer, but I hope you can see kind of the cursor going around. I'm in the middle of the page here. If the correlation is positive 1, remember it was a perfect square. If this correlation right here is negative 1, what we end up with is this first term plus this second term minus this third term, right? Because the correlation would be negative 1. So if that's the case, then the standard deviation of our portfolio, it's equal to the square root of sigma p, which means it's equal to the square root of what we had up above, and basically we've got WD sigma d minus WE sigma E. If we assume that the correlation is negative 1, we can simplify this variance and standard deviation down to this point. So remember, a correlation of negative 1, that means the assets are always moving in the opposite direction. So I'm going to write a few things. If the correlation is equal to negative 1 now, let's go back. Sorry, but I need to show you these things. Look at asset M and asset W, right? Asset M and asset W, they were always moving the opposite direction. When I formed a portfolio, if you'll notice, I was able to find a perfect hedge, wasn't I? I was able to find a portfolio, a combination that had zero volatility, zero risk. It was a perfect hedge. I can do that because the assets are moving in the opposite direction. So if my correlation is equal to negative 1, then we can find a portfolio that is a perfect hedge, i.e. where standard deviation is equal to 0. Okay, and it's pretty easy for us to find those weights, the weights that will do that. So let's go back and we'll start with this formula that we just had up here. We've got standard deviation of a portfolio if we assume negative 1 correlation is WD sigma D minus WE, the weight in E, times its standard deviation. Okay, all right, let's define WE to be 1 minus WD. Makes sense. 100% of our money is going into these two assets. So whatever we have in D, in this case, remember it was 70% in the previous example, so the amount we have in E would be 1 minus 70%, right? So now we can rewrite this and say the standard deviation of the portfolio is WD times sigma D minus 1 minus WD, that's represents WE, times sigma E. Okay. All right, let's distribute that. We're going to say WD sigma D minus sigma E plus WD sigma E, and we're going to set that equal to 0 because I'm looking for the standard deviation. Rather, I'm looking for the combination. We'll give myself a little room here. I'm going to move this over here. All right. I'm looking for the weights that are going to give me the weight in each asset that's going to give me the lowest standard deviation. So I'm going to solve for WD. Basically, this is an equality. I get all my WDs on one side, don't I? And I'll move this over here, solving for WD, sigma E in the numerator divided by sigma D plus sigma E. Okay, so let's plug in what we've got. Sigma E from our example, that was the standard deviation of asset E was 20%. The standard deviation of asset D is 12% plus the 20%. That gives us 20 divided by 32, which gives us and this is WD we're solving for, gives us 0.625, which means WE, the amount that we're putting in asset E, is 1 minus that, which gives us 0.375. Okay, so these are the weights in which we would be able to have a perfect hedge. Let's plug them into our formulas here. Let's solve for the portfolio return and the portfolio risk. Now it's an easy check because we're expecting our risk to be 0. Our portfolio return is that we're going to put 0.625% of our money in one asset that has an 8% expected return, 0.375 in asset E, which has a 13% expected return, and we get 9.875. When we plug these values into our formula to solve for the standard deviation, that's the weight in D times its standard deviation squared, the weight in asset E squared times its standard deviation squared. Then we would have plus 2 times the weight in the first one times the weight in the second one times the standard deviation times the correlation, which remember we're saying here's a scenario where we've got a -1. If we take this and calculate, you should come up with 56.25 plus 56.25 minus 112.5, which gives you a square root of 0, which is 0. So we have in fact found the combination of these two assets that would give us a perfect hedge. 62.5% in one, 37.5% in the other. This is only possible to get this perfect hedge because the correlation between these two assets is perfect negative. That's the only reason we can get the perfect hedge. Now, as we know, most of the time you're not going to find two assets that have a perfect negative correlation. We already said most assets are positively correlated. So while we might not be able to find a perfect hedge for each combination of assets, and I'll write it down because I think it's important. There exists an allocation that is a set of weights that will result in the lowest possible risk for that combination of asset. let me start for those two assets. Let me say that. Okay, and this is referred to as the MVP, which is the minimum variance portfolio. Okay, so for each combination of assets there exists an allocation. So asset D and asset E, right? Let's say the correlation is back to being 0.3, right? That those assets have a positive 0.3 correlation. There's an allocation. It's somewhere between 100% in one and 0 in the other, you know, or 0 and 1 and 100. It's some combination that when you add up those weights, you get, it's going to add up to 1. And that combination of weights will give you the lowest possible risk for those two assets given their correlation. Right. And so I'm going to show you how we get there. So I want to let's write down again the formula for variance. The variance of a two-asset portfolio, we said, is equal to the weight in asset D squared times its variance plus the weight in asset E squared times its variance plus 2 times the weight in D, weight in E, sigma D, sigma E, correlation between D and E. All right. Now, I want to, just because I know where I'm going with this, what I want to do is kind of expand this out. I'm going to go ahead and substitute in again that WE is equal to 1 minus WD. So let me do that. So I'm going to rewrite this. WD squared sigma D squared plus 1 minus WD squared sigma E squared plus 2 times WD, substituting in again 1 minus WD, sigma D, sigma E, the correlation between asset D and E. So all I've done here is I substituted in 1 minus WD for every place that you saw WE, which was the weight. Okay, continuing to expand, I'm going to take this 1 minus WD that's squared here and go ahead and use the FOIL method, go ahead and extend that. And so this is continuing on. I'll change colors here just for a little variety. WD squared sigma D squared plus, this is going to give me 1 minus 2WD plus WD squared. That's what, when I take 1 minus WD and I square it, it gives me 1 minus 2WD plus WD squared, all that by sigma E squared. I'll go ahead and distribute this next one as well. This is going to give me 2WD minus 2WD squared, all of that times sigma D, sigma E, correlation DE. Okay, so what I've got here is the variance of my portfolio is equal to this. Okay, so here's where we're going, and just hang on, all right? And I want you to see where this is coming from, and we're going to use a little calculus to get there. I'm not saying that I'm going to ask you to, to derive this formula, but I do want you to see where it is. All right. So what we're saying here is that the risk of a portfolio, the function, is measured by variance, is really a function of how much money we're putting in this case WD, because we've changed our two variables to one variable, right? It's not WD and WE. Everything is a function of how much we're putting in WD. That is, what percentage of our money we're putting in asset D. So basically I'm saying the risk of my portfolio is a function of how much money I'm putting in asset D. So what I'm going to do is I'm going to take the partial derivative of this function with respect to WD. So I'm going to take the first derivative with respect to WD, and I'm going to set that derivative equal to 0. You remember, if you take the first derivative, when you take the second derivative, if it's positive, you solve for a minimum. If it's a negative value, you solve for a maximum. When you set it equal to 0, we're setting where the slope is equal to 0. So I'm going to set this equal to 0. I happen to know that that the second derivative is positive, so I'm solving for a minimum. So again, taking the first derivative, this is going to give me 2WD sigma D squared minus 2 sigma E squared plus 4WD sigma E squared plus 2 sigma D sigma E correlation DE minus 4WD sigma D sigma E correlation DE. I hope I did that right, and I'll know in a minute if it doesn't work out. Let me just take a quick peek. 2WD sigma D squared minus 2 sigma E squared plus, let's see, hold on, 2WD sigma D squared minus 2 sigma E plus, this is a 2 actually, plus 2 WD sigma E squared plus 2 minus 4. Okay, I think I did it right. And I'm going to set that equal to 0. Okay. I'm going to get all my W2s. I'm going to get all of my W2s on one side. Alright, and so I've got all my WDs. 2WD sigma D squared. I'm going to move this term to the other side. Plus 2WD sigma E squared minus 2 sigma D sigma E rho DE minus 4 WD sigma D sigma E correlation DE. Alright, I think I'm good. Again, I'll know in a minute. I want you to recognize that I can divide both sides by 2. And I'm going to get rid of a lot of numbers, right? So I'm going to divide both sides by 2, and I'll get WD sigma D squared plus WD sigma E squared minus 2 WD sigma D sigma E correlation equals sigma E squared minus sigma D sigma E correlation DE. Almost finished with this. I'm going to factor out WD on the left hand side. and solve for WD. What we've just solved for here, these are going to give us the weights of the minimum variance portfolio. This gives us the weights. The amount of the percentage of our money that we would put in asset D that would give us the minimum variance. So let's plug in everything. Sigma E, that's 20 squared, minus 12 times 20 times 0.3, because that was our correlation, divided by 12% squared plus 20% squared minus 2 times 12 minus 20 times 0.3. I believe this gives us 328 divided by 400, which gives us 0.82. And so WD is 0.82, which means WE is 1 minus 0.82, which is 0.18. So what we have just solved for, given these two risky assets that are positively correlated at 0.3, we have solved for the combination that will give us the minimum weight, the minimum variance. We've said that we're going to put 82% of our money in asset E, 18% of our money in asset E. So solving for the return on the portfolio, if 82% of our money is going to earn 8 and 18% of our money is going to earn 13, the expected return on our portfolio is 8.9%. The risk of our portfolio, we need to plug it in and see. 0.82 squared times 12 squared plus 18% squared times 20 squared plus 2 times the weight of the first one times the weight of the second one times the standard deviation times the standard deviation times the correlation When I did this earlier, I got the square root of 131.04, which is 11.45%. So 11.45% is the standard deviation of the minimum variance portfolio. If we combine, given these two assets, asset D and asset E, and they have a positive 0.3 correlation, if we want to know the minimum possible risk, the least amount of risk that we can have, that we can gain by combining these two assets, the answer is 11.45, and it's going to come from having our weights of 82% in D and 18% in asset E. Okay, so that's going to be enough for now. This is looking at the minimum variance portfolio. We're not finished with this chapter. Where I'm going to go next time is I'm going to say, well, look, that's great, that's the minimum, but I may not want the minimum, right? What if I want to be more risk tolerance, right? Is there an optimal portfolio for me, given that I want this much, you know, I want to invest in these two assets, asset D and E, right? Help me find the optimal combination for me that's going to maximize my reward and minimize, while at the same time minimizing my risk. Okay, so that's it for now.